of money is $3.60. That's what I have. And so that's really this fancy science word, the superpositioning. And so don't get overwhelmed by this. This is just a fancy word that says, hey, superpositioning. They just combine together. Watch. Let's see if I can show you this, because it's really kind of neat to see. I can't really make the square wave that I drew on the board, but I can make two rounded ones. And so here's what I'm going to do. I'm going to make a rounded one, and it's going to go down to the end, and it's going to reflect back. So it will be coming this way. And while it is coming this way, I will make a second one. And so the two will meet right about here if I do this well. And watch when they meet. It's really kind of neat to see the superpositioning. And so I'll make one. When we get down there, I'll make the second right there. And right there again. And I guess right there again. And so as they come together, both of these are saying lift the rods up. And so maybe this one that's saying lift the rods up 3 centimeters, and this one over here says lift the rods up 2 centimeters. When they get there, you'll see them go really big. It is the superpositioning of the two. Okay? And how they overlap together. And that's why they get really big. I'll try this. It doesn't work real well, but I'll try the square one to see if you can kind of see that they do pass through each other. But I'll make the round one first. So it'll be a little bit of reverse of the picture I made. I'll make the round one. It'll go down and bounce and come back. And then I'll try to make a square looking one here. And you'll see if once they overlap, and then the square one continues on here. So here's the round one. And then here's the square one. And I hope that showed up a little bit. Maybe the one thing good about being in this position is you could actually then hit the space bar and stop it and actually move around frame by frame. So I'll be curious myself how it looks on video. This whole remote learning is new to me, as well as learning is new to you. So the whole teaching and learning remotely thing. But I'm hoping you at least saw that. And if you didn't quite see that in the little demonstration, I get that. But hopefully you see it in the picture here. In fact, let me keep going with this superpositioning, because what if this had happened? What if I had an up pulse going this way and then a down pulse, and let me try to make it the same shape, going this way. What would I get? And I'm going to say it's the same idea. It's superpositioning. Just combine them together. Now, of course, what's different, though, is these are telling the rods or the water or whatever the wave is, go down, and this one is saying go up. But when they overlap with each other, again, collide if you will, but when they overlap, you're going to get the combination of those two. And in this case, an up and a down tend to cancel each other off. And so right before they meet, it might look something like this. When they do fully meet, and so maybe I should point down here, I will get that. That's kind of interesting. And then a moment later, this down will continue on its way, and the up will continue on its way. So again, they just pass right through them. And so I'm not saying anything new here, but it is kind of a negative versus over here kind of a positive. Because here the combination is up bigger than any of the two separate. But here, because one is positive and one is negative, they tend to cancel each other off. And so again, this is a neat behavior of waves. In fact, sound waves, you might have noticed this as well as this the best. because waves don't bounce off each other. I'm sure you've been in a group of people talking. And so let's say you're just all, and this would be pre-coronavirus, so, you and a bunch of friends go to a restaurant, and there's 6 of you hanging out at a table, having a good time, talking. And as you're talking with somebody across the table, you have never, ever said, "Oh, could you repeat that? I didn't hear you." Bob's sound waves hit and deflected yours and knocked them out of the way, and they didn't get to me. See, that never happens. The sound waves pass right through each other. And so as you and I are talking, Bob and Louise are talking here. And so they're talking and we're talking, and our waves just pass right through each other. And so that's what I'm trying to illustrate. That's this superposition. Now, I should emphasize this, though, of course, is a negative. If my example of money holds true, this would be a little bit more like, okay, so somebody asks you how much money you have, and you go, "Oh, yeah, well, I have $3 in my wallet or purse. I have 50 cents over on my dresser. I've got a dime in the cushion there, so that's $3.60. That's what we said before. But then you remember, oh, wait a minute. I had borrowed $3 from Louise the other day. We were at school, and I needed to buy some supplies at the bookstore. So actually, I have a negative $3 there. Okay, so how much total do you have? And I would say you're doing the superpositioning of all your money. 3 plus 50 cents plus a dime, that's $3.60. And then minus the $3 you need to give Louise the next time you see her. And so you really only have 60 cents. That's your net. That's your superpositioning. And so that's what this is trying to say here. And so the whole reason I tried to draw this up and this down the same shape, because if this is saying lift the rods up 3 and this is saying push them down 3, what you would get a flat line is right there, and you would get nothing. And the reason I said you might have observed all of this before in sound waves is because somewhat common are these noise canceling devices. Earbuds, headphones, some of the really good quality ones. Like there's this Bose pair that I love to play with when I go to Fry's. I can't afford it, but I love to play with them. And you go in there and you put on the headphones, and they're headphones. They're not earbuds, and so they cup your ears. And so part of the cupping of your ears is it just blocks the sound waves. And so you're in this big warehouse type store, you put it on, and that cuts out about half the sound right there. And so there's a lot of noise in the store, and so that just goes away. But you can still hear all the commotion in the store. It's just muffled, if you will. But then they've done something really clever, and they've taken advantage of this superposition. And the reason it's called noise canceling is because then the engineers inside have a little microphone. And what that microphone is there for is so it can pick up what sounds from the outside are actually getting inside of here. Because then whatever sounds get inside, the speaker on those headphones then will take that sound, say this is the sound that gets in, and it will produce what I'll call equal and opposite sound. It'll produce a sound that goes the other way. And so it'll direct it right into your eardrum. And so right at your eardrum, you're getting this. And so it's taking the noise and it cancels it off. And so we call these noise canceling headphones here. And to me, they're amazing. Like I said, when they're done really, really well, the earbuds don't do it quite like, and maybe it's the quality of mine, but do not do it like these Bose headphones. I mean, I find it amazing. In fact, instead of listening to the music, I like to do this. I go in there, I put it on, and then I like to listen to, the rest of the noise. Usually maybe there's a bunch of kids running around over here in the video section, so they're zipping around. And then I turn them on, and it just goes dead quiet. And then I turn it off, and then I can hear the noise. And then I turn it on, dead quiet. And then I turn them off. And so it's just taking that noise. Now, of course, the other thing is you're supposed to then turn them on and then play some music so you can get a feel for them and see how enjoyable it would be to have these headphones to listen to music without hearing all the noise in the background. But like just the scientist and engineer in me gets all excited. I go, these are just amazing. In fact, a little background for me. I did my graduate research thesis connected to this. It goes back, way back when I was in graduate school, so this is about when the dinosaurs were still walking on the earth here. But stealth technology was still unproven, undesigned. And so we were working on how to make an airplane invisible. And this is one of the things we added to it was, hey, what if we did this? The way an airplane is normally viewed is you put a radar station and you send out these radar waves, and then you have this airplane up in the air, and the radar waves hit the airplane and reflect off and come back to the receiver, and that's how you know the airplane is there. So what if at the same time that these radio waves hit the airplane had a transmitter that produced waves in this fashion, and so what goes back to the receiver are two waves, a combination of this, which is I'll call it the normal reflection that would have happened, and then the waves that are produced by the electronics on the airplane that cancel it off. And so what ends up getting back to the receiver is a cancellation. And of course what the receiver would do is then say, okay, I'm not getting any signal, and without any signal I have a cancellation. They don't know it's a cancellation. They just think there's no airplane. And hence the airplane is invisible here. Although maybe I should add to this that despite our word about stealth, that's an overrated word. This is not stealth. We cannot do this perfectly well. We do the best we can. And you get something that is not exactly zero. So if the airplane is close enough, this would be big enough that you can detect it. So planes are not really stealth. They're low observable, which is just as good, because if you stay away from that radar station, they don't know you're there. And so as long as you're 10 plus miles away, you're fine. And so good news is they couldn't pick you up until you were 10 miles close. And so they're not picking you up hundreds of miles away. They're only picking you up when you're within 10 miles. Maybe a better example of this, though, is water waves, because we live here in the on the beach here. And if you look at the waves coming into our beach, you'll see what looks like, oh, here comes a bunch of waves, then no waves. Oh, here comes a bunch of waves, then no waves. And I would say it's a little more interesting than that. It is not quite that simple. It is a combination of this superposition. And here's what it is. You have lots of waves coming into your beach. I'll just simplify it and say two sets. So let's say you had two storms. You had one in the Central Pacific and one in the Northern Pacific. And so as the waves come in and come to our coast, how they come in, how they align, how they interact, they may interact like this for a while, and then they may interact like this for a while. And so what you would say here is when they're interacting like this, you would have this buildup. You would have big stuff crashing in on your beach. And that's when you get all excited and you like, okay, the surf is in. This is when you're hoping, okay, I've already paddled out and I'm ready to catch that wave. And so you've gotten yourself in position. But a few moments later, after these few come in, you would call it a set, you get a lot of this flatlining stuff. And now you're just hanging there. You go, oh, no waves are coming in. And I would beg to differ and say that no, the waves are coming in. They're just not adding up right. They are then subtracting from each other. And of course, that's the time you want to paddle out. And so you paddle out during this time. And then you wait, and then hopefully if things work just right, then you hit this. And then you let that kind of die out and you paddle out again here. And so you take advantage of that superpositioning, and so we kind of subdivide this then into categories where we call this then a destructive. And sometimes we use the word interference. I would say that interference is just the overlapping of waves, and so just as equal is this word called destructive superpositioning, destructive interference. Whereas over here, because they are adding together and getting bigger, let's call this then constructive interference or constructive superpositioning. And in fact, that word constructive interference, I think, catches some people off guard. They look at this like, well, wait. Interference is supposed to make things smaller. No, that's not quite how a scientist or an engineer would use it. Interference means we have this overlap of waves. This could make things smaller and therefore harder to detect or harder to pick up. Or they could make them bigger. And so we've got constructive interference and destructive interference. In fact, my cell phone, I noticed this really well here on campus with my cell phone. If I walk out of this building, just right outside, and I hold up my phone, I get 3 bars really, really well. And my first reaction is, oh yeah, well, I'm not far from TV Hill here, and there's a transmitting tower right there, and so TV Hill just puts it right down here on campus, and I get a strong signal. And although that's true, there's a lot of buildings here, and so I get a lot of reflections off the building. And it so happens that right outside here, I get one signal directly from the transmitter, I'll call it TV Hill, and I get another one that reflects off of our building, and they add up this way. I get a superposition. I get a really strong signal. Because I don't have to walk very, very far, maybe about 200 yards over to my left here, and I look down at my phone and the signal just really drops away. And what's really weird about it is I can even see the transmitting tower. I can even see TV Hill. I'm like, how can I not be getting a strong signal? I can see it. And of course the answer is, I've got more of this. I've got the signal that's coming directly to me. I can see it. But I'm far enough away from the building that after it bounces off the building and comes to me, it's doing something like this. And it really drops it. Now, not to 0, because the reflection is not that strong. And so I get, not a complete cancellation. And so I go from 3 bars down to 2 bars here. And as I just walk across campus, you can kind of get that approach. In fact, a fun game I like to play, not so much now. My kids were younger, to go see Grandma. And so my parents, when they retired, I grew up in the LA area, sold and moved out to Arizona, where things were a lot cheaper. And so to take the grandkids out there, I would have to drive, 8 hours or something to go see them. And when they were really younger, we decided, maybe the best way, my wife and I go, maybe the best way to travel with them is while they sleep. So why don't we, put them in their PJs, get them nice and close to being tired, and why don't we hit the road about 7 or 8 o'clock in the night, and we'll just drive through the night, and then they can just sleep through the night, and then we'll get to Grandma's. And we'll probably be tired, but we can sleep when we get to Grandma's, and Grandma can watch the grandkids. So that's how we would travel. And of course, it would get really late, and so it's 1, 2, 3 in the morning, and I'm out in the middle of the desert getting tired myself. Kids are asleep. Wife falls asleep. I'm all kind of alone. And then I realized as I was listening to the radio that it would fade in and out. And so many times, to keep myself awake, the curiosity in me would say, all right, there is a transmitting tower, and I would usually use KFI. It's 640 kilohertz out of Los Angeles. And as you're driving along, if you listen carefully to it, it'll fade in and out. And the reason why is you're getting a direct shot from the radio tower in LA, but in addition to that, it's bouncing off the ionosphere. And so up here on the ionosphere, you are really getting something like this. You are getting a superpositioning. And as you drive, the distance gets greater, and so this reflection here puts you sometimes when you get this, and so you get constructive interference, and you can pick up the radio station really strong, and later on, you can pick up this, and it really diminishes. And of course, if you keep a track of your distance, how far you travel, and of course, if you know the radio station, you also know its frequency, you know its wavelength, and so a few calculations later, you can figure out how high the ionosphere is. And so this would keep me entertained for a few hours as I was driving along, and I would mark my little book and data, and then I'd just keep going, oh, I don't know, okay. And so by the time it faded in and out 5 or 6 times, I could do a calculation, and wasn't easy while you were driving, and that was good because it took me a long time. And then I would try it again about a half hour later and see, okay, is the ionosphere at the same height? Did it change as it's cooling down? And so anyway, that a side note, that's just my personal weirdness of it. But it does illustrate the constructive and destructive interference that you'll get also with the radio waves. And that's what I'm trying to emphasize here. We are talking in this chapter about the generalization of waves, but I want to emphasize to you, this is true for all the waves. I could talk about radio waves, I could talk about X-rays, I could talk about light waves, I could talk about sound waves, I could talk about water waves. All of these waves have these overall properties. And that's what I want to keep emphasizing here. This is not just unique for these waves. Well, I've been talking probably way too much, and I haven't got a chance really to kind of show you this. So let me come back to our wave machine and see if you can see it. This one, if you thought the constructive interference was hard to see, this is really hard to see. Now, fortunately, the constructive with the 2 round humps is easy to see. In fact, maybe I'll show you that one more time since it's been a few minutes since I saw it. So if I made a rounded one and then another rounded one right there, wham, see how big it gets. That's our constructive interference. But the one I want you to see, and the reason it's so hard to see is, first of all, I have to make an up and a down hump, and the better I make them the same shape and the same size, the flatter this is going to get. But even if I do that perfect, watch this. What does it look like right before and right after? And this is a visual effect that I guess would fit under that category of optical illusions. You know, have you seen things that just aren't true, but they look that way just because of the things around them? When you have an up and a down, let's say it's just 3 centimeters, when they get right here, you're going to have your up 3 and your down 3, and they're going to be one big slope here, and so from here down to here is going to be 6. And I think it gives a little of an optical illusion, like, hey, it got bigger for a second. No. It didn't get bigger. You just kind of lost the intermediate step as it went down and then down again. And when you visually see this as one big drop, you go, hey, it's big. And then, of course, after they pass, you have the same optical illusion that this is up and this is down, and that looks like 6. And so it almost looks more like this. This is what I'm going to ask you to kind of look for, is as they approach each other, see if it doesn't look big, small, big. And know that these are an optical illusion, and that small is what you're trying to see. The destructive interference. All right, so like I said, not so easy to do, but I'll make an up. It'll go across, and when it come back as an up, I'll make a down that tries to match it. So I'll keep my eye on it here and see what it looks like. So an up and a down. Right there. Oh, right there. Did you see it? And maybe this is a good thing on the video camera. You could play it a little slow. I'll try it one more time, but you really just kind of have to humor me. When I'm in a face-to-face class, I say, hey, just humor me. Say you saw it. All right, so I'm going to try it again here. So here is an up, and here is a down, right there. So it's like up, flat, up again. Yeah, oh good. I'm glad you guys are humoring me. So whether you saw it or not, hopefully you can see it in the drawing here. I'll do one more. This one is related to sound waves. But like I was saying, for water waves at the beach, we don't really notice, at least the general public doesn't notice, that it's a superpositioning. And the same thing here with our sound waves. If I were to take and let me not say too much about these tuning forks yet, because this will be the next lecture as we get into the next chapter on specifically on sound waves. But I can hit this, and I'm hoping you can kind of pick up the sound of this on my lapel mic. And if I do the other one here, and I'll maybe get a little close here with my lapel mic, and maybe you can pick that up. These are two different sound waves. But if I were to draw their picture, they have a slightly different wavelength. And the reason that's important here, and so if I go, here is wave number 1, and here is wave number 2. And so wave number 1 maybe looks like this if I were drawing a graph of it. And wave number 2, I'll kind of exaggerate, has maybe a longer wavelength, so something like this. And then if I make both of them at the same time, so both of these make sound, come out, merge together. And so what I will be picking up with my ears, and hopefully you'll be picking up on this microphone here, is the overlap or the superpositioning of these two. And if you look at this, you'll see that maybe on this part right here, the up goes with the ups. But because they're of different sizes, later on, an up of this wave will be corresponding with a down, so a crest with a trough. And then that would be what we would call destructive interference. And so at the points where we have constructive, maybe I'll even make it bigger. And so at the beginning part here, the up goes up and then the down goes, and I should have made this not quite so big, but that down would be with that down. They would be in sync with each other. Ups would go with ups and down would go with downs, and so you would get something that looks like this. But as we go along, the ups here would correspond to the downs here. Then it would go down, this one would go up. And in fact, I'm just going to draw a little tighter picture. I wanted to emphasize they were different wavelengths, but I did it so much that you don't really see, if I did that an up goes with an up and a down goes with a down. And that works fine for a little bit. But eventually, they get out of sync. And an up, a crest, goes with a trough. And so you get destructive interference. And then, of course, if you continue along, you get constructive again. And then destructive. And so the combination of the two together has this switching between constructive and destructive interference. And you can hear that with your ears, since, again, these are sound waves, not the water waves. And so, again, if you're out at the beach, you would see that. You would see lots of waves, no waves, lots of waves, no waves. And usually at the beach, you know, those are about 10 to 13 minutes apart here in our part of the world. It depends on the storms, and it actually tells the oceanographer and the meteorologist a lot of information about those storms. So I'll try the two together. And so can you hear that kind of pulsating? Now, when it comes to music, if I had a bunch of instruments playing and they got louder and softer and louder and softer, I would just call this the beat of the music. But that word goes beyond sound waves. We in science use the word beat for this rate at which it goes constructive to destructive, constructive to destructive. And so beat is an appropriate word when it comes to sound waves, but I'll go you one better. When I go out to the beach and I wait for 10 minutes between sets, that is called the surf beat. It is the rate at which I go from constructive and destructive interference. So this word beat, you know, it's probably not a new word to you. When you apply it to your sound waves, but it is something that is new, I think, if I was going to apply it to water waves or to radio waves or to light waves. And so again, this is just referred to as the beats. Now, I haven't given you a chance to really work with some numbers here. This beat, though, the rate at which it goes back and forth is actually then the frequency of the first one minus the frequency of the second one. And since I don't want to decide which one is the positive or which one is bigger than the other, let me just put absolute value, but this is referred to as the beat rate. It's the difference in those frequencies. So this one, as we will get started in the next chapter soon, goes back and forth 256 times every second. This one then, if you listen to it, maybe about twice a second different between that one. So this would tell me this one is either 2 more or 2 less. So again, if this is 256, this must be 258 or 254 as they overlap with each other at a rate of 2. And so that's the difference in their frequency. And you can kind of see it here in this picture. It's the difference of how those line up. Well, again, I should keep going here and talk. And one of the things that I just realized as I put the word frequency on the board is that you might have recalled I defined the word frequency for you last chapter, but we weren't talking about, not last chapter, last lecture, but we weren't talking about waves at that point. We were just talking about a single object oscillating. But let me assure you it's the same definition. And so this would be a good time for me to point out that as this wave oscillates and it goes up and down, and I draw a kind of a little picture here. So here's my wave and here it is oscillating. And so in today's lecture, I talked about the crests, I've talked about the troughs, I've talked about the wave length. But remember those other 3 words we talked about, the frequency, the amplitude, and the period. Those still apply to our waves. And they have the same definition, and that's why I kind of just real quickly just said, oh yeah, well that's the frequency. But I thought I should pause for a moment and say, wait a minute. I hope the students get what I mean by the frequency, because when I was doing frequencies yesterday, I had like the little pendulum here. In fact, that's the lab we're going to do today, is the pendulum one. And as it swings back and forth, you know, you could talk about its frequency, its period, its amplitude, and we did. But I can do the same thing with these little rods. They would go back and forth. And if I just looked at one rod and say it went up and down 3 times in 1 second, I would say it has a frequency of 3 hertz. And so back to this little tuning fork here, when I get it started, I left my left my striker over there. Maybe I'll go get it, because I don't know if that's enough to really kind of hear it. But this would say that this little metal piece right up here at the top, what we call the tuning fork, this goes back and forth 256 times in 1 second. So that's the frequency of it. And of course the reciprocal of that, as we talked about yesterday, is the period. And we also have an amplitude here. That it would be, in this case, how high the rods go from equilibrium. And so if I put it in this picture over here, this would be then the A, what we talked about last time, the amplitude. And I'll say it again, remember the amplitude is not the total difference from the one extreme to the other, or in this case vertically. So from top to bottom is not the amplitude. The amplitude is from equilibrium to the top, or crest, or from equilibrium down to a trough, the bottom here. And so I will continue to use those same words. Well, how are we doing on time? Oh, good. And we're almost done here with the chapter here. I probably should put a little more equations in here. For example, we learned, albeit way back in chapter 2, about the concept of velocity. And let's apply that now to our waves. When we learned it before, we were doing mechanics, and so we were talking about, you know, like a car's velocity. And so this is not a mechanical movement. And I'll say it again, waves are the flow of energy, not the movement of the material.